Good morning. My name is Marco Bouterse.
And I'm Yana Mateeva.
And we are graphics programmers from Nixon Software, part of PlayStation Studios. Welcome to our talk about bringing Ghost of Tsushima to the PC platform. For those of you that don't know the game, Ghost of Tsushima is an open-world action-adventure in which you play as a samurai fighting off the Mongol invasion of Tsushima Island. The original game was released in 2020 for PlayStation 4 by Sucker Punch, and a Director's Cut edition was released in 2021 for PlayStation 4 and 5. It adds a whole new playable island and some graphical improvements. And the PC version was based on this version. As you can see, this game looks absolutely amazing, and we were very excited to be able to bring it to PC. Today, we want to bring you along with our development process, starting at the very beginning, present some of the building blocks that we needed to implement all our render systems, tell you what we need to do to make it a fully featured PC game, and finally we will present some of the optimizations we needed to do to make it run well on a variety of systems. So, let's start at the beginning. This engine had been on PlayStation for a very long time, so there was no PC code at all, there was no platform abstraction, async compute was extensively used to improve performance, and the unified memory system of the PlayStation was fully exploited. All in all, this game was extremely well optimized for PlayStation, so we knew we had a major challenge ahead of us. To illustrate, a lot of our previous project always had an engine setup where there was some kind of cross-platform render API in the engine that all the platforms were implemented against. And usually there was already some kind of PC implementation, either for tools or for some other purpose, that we could use as a starting point for our ports. However, Ghost of Tsushima did not have this, and all the engine code would just directly call into the PlayStation API whenever it needed. So what were we to do? Should we invent our own cross-platform render API? However, we just got this project, we don't know this engine, so we don't really know what the right level of abstraction is to make here. Also, this would have been a monumental effort from us. So we had this other crazy idea: what if we use the PlayStation API itself as our abstraction layer and use DirectX 12 to implement it? Surely this won't work because DirectX is higher level than PlayStation API, right? But first, we have to take a few steps back to the actual beginning. We needed to get this game compiling for PC because there was no PC platform at all. Luckily for this, we had a secret weapon. Bruce Oberg, co-founder of Sucker Punch, joined us for a few months at the Nix's office to help kickstart this project, get the game compiling, get us to the main loop, set up build servers, and much more. Thanks to him, we could really kickstart this project. So after this compilation phase, we ended up in this situation where we just stubbed out all the PlayStation API functions with empty implementations. The very first thing that we needed to do was get up a window. Luckily, we have a shared game-agnostic library at Nix's called NXApp that makes it simple. It handles swap chain and window creation and much more. And it gives us a DX12 device and a graphics queue. So at this point, we are finally ready to start writing some render code. So for our first render goal, we wanted to get the debug rendering and the debug menu up, because this is relatively simple. So we started with implementing a PC command context, which is a simple, lightweight wrapper around the command list, and here we were able to hook up all our command list creation and submission functions. The very first thing that we implemented here were the debug markers, because that gave us the opportunity to already take render docs and pix captures and see the entire frame laid out in the markers, even though nothing was happening yet. For the debug rendering, at this point we just hardcode everything, just put in DX12 calls wherever, and we set up our shader compiler to only compile the debug shaders we need and compile everything else to a dummy, and we bypass all the PlayStation specific paths in the shader. We also use T3D12MA to bootstrap our memory management at this point. And with this, we finally have our first debug geometry captured in RenderDoc. To get the debug menu working, we also need a font texture. And to get this, we just grabbed a PlayStation GPU frame capture, saved out the font texture to disk, and loaded it straight from disk, bypassing all the engine loading functions because those were not up yet at this point. And we set up some render state. And after a few iterations, we finally had our debug menu. The next step, we wanted to render something for real. So we found the simplest possible test level, which contained only a single red cube. And to achieve this, we needed some building blocks.
So we want to render a single cube. What do we need? So first of all, we need to actually be able to load into a level. Thankfully, Bruce already set us up there. Then we also need to hook up some very basic physics and gameplay data and other things that we don't really care about, but we kind of have to do it because we're the only 2 people on the project. And then the fun stuff, we need some geometry, we need some shaders, and we need some textures. Let's have a look at how it works on the PlayStation. So the content for PlayStation is divided into data packs, and these get loaded directly into both CPU and GPU memory, and they contain PlayStation-specific texture and buffer descriptors. Pointers get patched at runtime to point to the correct data, and there's not really an explicit point of time where resources get created. This is possible because the PlayStation hardware has a unified memory architecture, and what that means is both the CPU and the GPU can access the full memory range. The resource descriptors on PlayStation are essentially just fat pointers, and so creating a lot of small and short-lived resources is very, very cheap. A very simple illustration of how that looks like, we have a giant memory block, and both the CPU and the GPU have full access to it. And on PC, it looks something like this. We have our system memory that the GPU has access to, and we have our video memory for the GPU, and then all communication between the 2 goes over the PCI Express. More specifically, in DX12, we have a default heap in GPU memory, and then to upload data from the CPU, we go through an upload heap. To read memory that the GPU has written, we go through a readback heap. So how do we handle resources on PC? Because we need an explicit point of time where we create and destroy resources, and this can have pretty significant overhead, so we have to be very careful where and when we do this. We also need to use upload and readback buffers to interact with the memory on the GPU. We're bound by minimal resource size restrictions, so we have to be very careful with our suballocations. And also we need to take care of oversubscribing on video memory, because then memory can be demoted to system memory, which makes GPU access very, very slow. So on PlayStation, we directly load a hardware descriptor from content. It basically is some metadata. So for a texture, it can be the width, height, and format. And then it also has a pointer directly to GPU memory. We're using the same data layout on PC. So we have this situation. We have a descriptor with the same metadata, but it points to CPU memory. So how do we get it to GPU memory? We set up something like this. So, of course, we create our D312 resource. It points to our GPU memory. Then we schedule an upload from the CPU. We have a little wrapper around the D312 resource, plus some additional DirectX 12 goodies that we need, like resource state tracking. And as soon as all of that is done, we can patch our descriptor to point to our PC texture instead, because we don't need the CPU memory anymore. For buffers, we take a similar approach, except our descriptor is actually too small to store a full pointer here, so we have to go through a 32-bit hash table. Why do we take this approach? Well, we need to make very minimal code changes on the engine side, and most importantly, we can use the same data layout on PC. And at this point, we're really at the stage where we're just saying, okay, let's make it work first, and then we'll improve it later when we need to. And with all of this done, using some debug visualization, we can see the geometry of our cube. But if we want to actually see it for real, we're going to need some shaders.
Yes, and those shaders were giving us some trouble because we were dealing with some unsupported language features like lambdas, platform intrinsics, assumptions about wave sizes, but most importantly, pointers. So how did that look? Here's an example shader. And what we see here is we have a struct that's passed by pointer to the main entry point. Pointer access is used into this struct. Also, the struct itself has a pointer member that is accessed here, and resources are also in the struct and are used here to sample a texture. What we see here is a PlayStation shader concept called shader resource tables. It's basically a struct containing both constants and resources, and it's a super convenient way of passing your data from C++ to the shader, because you don't need to explicitly bind any resources, and you can directly write the descriptors into the struct. It works by passing a root SRT to the shader main function, and this root SRT can also contain pointers to other SRTs, so other structs. So on PC, this was a bit of a problem, because we cannot pass resources like this, and HLSL does not support pointers. So do we need to rewrite all the shaders for PC? First, tackle resources. We actually have a solution for this problem because we can use bindless and just store a heap index. To facilitate this, we created a little proxy struct that wraps the index and provides the original resource interface, so we can use it as a drop-in replacement for the original resource. And we have some defines around that. So on PlayStation, it directly goes to the actual resource, and on PC, it goes to our proxy. So here's an example of our texture proxy. We store the heap index with some padding to make the descriptor, or to make the struct the same size as the PlayStation one. We have the main function that gets the resource from the heap and casts it to the right type. And then we have all the original interface that just passes on the function to the original resource. So how do we get the root SRT to the shader? Our first implementation used a structured buffer because we cannot use constant buffers. They have more strict layout requirements. But this still had some limitations because we need to have a separate one in every shader for each different struct type. And it also doesn't solve our problem of having pointers inside these structs that point to other structs. So our biggest problem was, how do we support those pointers? Luckily, we came up with an idea. We can emulate these pointers as offsets within a buffer as long as we can put all these structs in the same buffer. And we can actually do this if we use a byte address buffer and template loads. That way we can store different structs in the same buffer. It works from C++, and we can convert all our pointer use to offsets. This worked so well that we also used it for our root SRT. We just pass an offset as a root constant. And using this, we can actually have multiple SRTs per shader file, and we can also support different shader stages using a different SRT. So how do we deal with the pointer syntax itself? We considered some alternative solutions like a custom preprocessing pass or even modifying DXC. But we chose a pretty low-tech solution and just wrap everything into regular macros. And we chose to dereference the pointers as soon as possible, so we can just use regular access afterwards. So here's an overview of our macros, mostly for reference here. Let's zoom in a bit on the load ones. On PlayStation, you can see here that the pointer that's passed in is directly dereferenced. And on PC, this is actually an offset into our buffer. So let's go back to our example shader. Here we apply our resource proxies. We actually already had these defines in the original code because there were some Maya-compatible paths in there. So that helped us get on our way, and we could just plug it in to these defines. And then we apply our SRT pointer macros. We wrap this one. This just stores the offset on PC. This one does nothing on PC. And then we just load from root constant here. And the pointer load just enters the offset and loads from there. So how does it look from the C++ side? We have a per frame CPU visible buffer in upload memory. And during the frame, we have a simple linear allocator, just allocates all our SRTs from this buffer. And whenever we need to draw, we store the offset to the SRT as a root constant. So here's a quick code example. We allocate one of these structs, so we get a pointer back to the buffer. We fill the struct with our proxies, and then we bind it, which sets the root content, and then we're ready to draw. We just had one problem at this point because DXC did not fully support it. If you try to load a struct with the templated load, and that struct itself contains a type that is templated, then it doesn't work. And all of our proxies that we put in there were templates. So we filed a GitHub issue, and it was fixed within 2 weeks. So this was actually really great. Yeah, great job by the DXC team. So we were able to continue on this approach. So let's evaluate our approach. There are some pros here. We can stay really close to original code. We can keep sharing the same shaders between both platforms. It's a rather elegant solution, but most importantly, it actually works. There's also some drawbacks. It requires shader model 6.6 to do the bindless. And at this point, we didn't really know if that was going to have any impact on our min spec. It makes debugging a lot harder. I will show you in a minute. And also opens up to a lot of potential for GPU hangs. Also, there was not, at this point, we don't really know how it's going to affect performance in the end. So let's have a quick look at the debugging. If we want to see our constants in pics, we have to hunt down our root constants. We have to memorize or write down this value because you can't copy from this field. Then we have to find our buffer. We have to fill in the offsets. We have to apply a custom buffer formatter for all our structs. And then we can finally see our constants. So it's a bit of a hassle, but with all this hard work done, we are now finally able to load into our cube level and then open a debug view because we didn't have any lighting or anything yet at this point. But now we can see the albedo debug view of the G-buffer, and we can finally see our cube.
So great success. We have a cube. Now we need a new goal, and for this we decide that we would really like to render the main character. So we pick a new test level, and this one turns out to be big enough to warrant a loading screen. And it kind of looks like this. So let's have a look at textures. Turns out that pretty much all textures in this engine use MIP streaming, and there's not really an easy way to bypass this. And the base MIPs are only 64 by 64. So to avoid having our eyes bleed every time we look at the loading screen, we decide, okay, let's just bump that number up a bit. So we increase the base MIP size to 256 by 256, and now we have a slightly less blurry loading screen. However, our VRAM usage is absolutely through the roof, and also the loading takes absolutely forever. So do we go back and just deal with the blurriness for now? Maybe that's the responsible thing to do. However, at this point, we are still two mostly unsupervised graphics engineers, so we decided, no, let's just move forward and look at texture streaming. So on the engine side, there is some math in place for MIP priority calculations that on PlayStation uses Clang vector extensions, but we're using MSBC. So we had to implement the vector math ourselves. And on the DX12 side, we have a very simple model for MIP streaming. We have our current texture, it has a couple of MIPs, and then we need to stream in some new MIP data. So we create a new texture that's big enough to store everything. We schedule copies on the GPU for the data that we already have. We schedule an upload from the CPU. And once all of that is done, we just throw away our old resource. Now we have a crisp loading screen, which finally gets us here. We can see Jin here T-posing. Of course, we would really prefer if he were animated. So for that, we're going to need skinning. So first of all, we need to enable the shader code. We already have our handy-dandy macros, so we can do this. And then we need to update and bind the skinning buffers. The binding part we already have solved. We can pass our resources through the SRT. However, it turns out that the update is actually the trickier part. We're still fully on this approach, so we're directly implementing our backend under the PlayStation API, but we're finally hitting the limitations of this because on PC, we just have much more complex interaction. So we plug in a teeny tiny little abstraction layer specifically for buffers. What this does is it basically only adds a single flag parameter to our buffer creation. The rest of the API fully mimics the PlayStation still. But now this buffer abstraction can contain two buffers on PC, one for the CPU and one for the GPU. It can handle the view creation, and we can specify whether we want transient or persistent descriptors. We can pass in sub-allocation hints so we can manage our memory a little bit better. And we also don't need to go through a hash map anymore. And now we can finally see Jin running around. A few more things we need to have as our building blocks. Let's look at our descriptor management. So what we do is we allocate one giant descriptor heap using the maximum possible descriptor count minus a few reserved for tools. And then we divide it into three parts. The first part is for persistent descriptors. Those we manage the lifetime of explicitly. And then we have two parts for our transient descriptors. The CPU is writing to one part, the GPU is reading from the other one, and then on the frame boundary, we flip the two. We also need to make sure that our resource states are correct. And unfortunately, the engine doesn't provide us with a frame graph. So we mostly had to manually place our barriers. And because we are heavily using bindless, we didn't really get a lot of help from the validation layer. So what we often resorted to doing is taking pix captures, looking at the passes that we're currently working on, and then checking the resource history to make sure that we're using all of our resources in the correct state. So what's next? We finally have our building blocks. Now we just need to apply them. So we finally move on to a more challenging test level. And now we need all of our render systems. Unfortunately, we don't really have a magic abstraction switch. We need to go in and touch up manually every single system. But this was a really fun part in the project where we could finally see all of the features coming together one by one. And to actually see them, we did put in a temporary light shader so that we can see things without looking at the gbuffer albedo. This is a non-exhaustive list of all of the systems that we had to manually tweak to get running. The developers over at Sucker Punch have already given several great talks on a lot of these systems, so we're not going to go in depth into any of them, but I would highly recommend giving these a watch. So now we're here. We looked at this and we asked ourselves, what are the systems that we absolutely need to have in place to have a playable game? So maybe quite obviously, we need to have some terrain. For that, we first hook up some geometry. Then we run into some issues with our GPU index buffer generation. Finally, we get some clip maps rendering. And after some final issues with terrain blends, we can finally have our terrain. The next system that we decided is absolutely crucial are the proxy sets. The proxy set system in this engine is a system that handles culling and rendering of objects with very high instance counts. So most trees, flowers, rocks, etc., and many more get rendered through this path, so the world looks very barren without them. The proxy set system is a very complex system, and especially so on PC. It was the first system that we tackled that absolutely required async compute. It has a round trip to the CPU to read back the instance counts from the culling pass. There's even a shader on PlayStation that directly writes out buffer descriptors, but unfortunately on PC we had to bypass that and do it the lame way, just allocate buffers on the CPU. There was very heavy use of wave intrinsics for optimization, and just overall, by far, it was one of the most challenging systems to get performant on PC, but we'll touch more on that later. But with both of these systems in place, we can finally load into the open world. Unfortunately, we did run into plenty of data issues. These were mostly related to packing differences between Clang and MSBC. But our building blocks were finally being used at scale, which did prove that they work. However, we did need to do an initial optimization pass to make sure that we're running at a playable frame rate. So we compiled a short video that, we mostly took these videos during development, and the progress is really nice to see. All of these systems did come with their own unique challenges on PC, but it's out of scope for this presentation to go through each one specifically. However, if you have any questions about any specific system, we would be happy to answer them after the presentation. This was a great point in time when we could finally throw away our temporary light shading and finally enable the real thing. Then we finally got to move on some more atmospheric effects. The water in the ocean rendering system actually uses tessellation in this game. And finally, some post-processing pretties. So one thing that you may or may not have noticed was not in this video was the particle system. And as in any game, these are obviously very important. However, in this game, the particles are used to visualize the wind, and the wind is actually used as a guiding system for the player. And it's even used to render some small animals and distant enemies. And because Marco was convinced that he could implement this in a month, I'll let him explain why that didn't happen.
Planning is hard. It actually took like 3 or 4 months, I think, in total to get all the bugs out. So let's have a quick overview of the system. Why was it so hard to port? There's a great talk actually from Bill Rockenbeck from Sucker Punch about the original particle system, which was created for infamous Second Son, the previous game from Sucker Punch. It's a GPU-based system, completely in async compute on the CPU timeline. So it sends jobs from the CPU to async compute and gets them back and then prepares the next frame. It's based on an expression-based language that's compiled down to shader code. So you can do very cool effects in it. And all the translucent particles are sorted together and drawn in one single draw call. Some of the features are stitched particles or ribbons, UI particles, animated meshes, and all kinds of distortion and displacement effects. And it's also capable of generating real light sources, sounds, and can influence the wind. So the toolchain looks a bit like this. You have this expression-based system that compiles down to shader code, and it gives us an emit compute shader and an update compute shader at runtime. The emit compute shader outputs particle state, the update shader updates it, and there's a feedback loop so you can read the previous frame particle state. The update shader then outputs some draw records that can be used to draw the opaque particles, but also goes into the single pass translucent draw, which of course needed to be sorted, so the update shader also outputs sort records. These are sorted in a separate compute shader, and then the output is sent to the translucent draw. So what were the main challenges here? Again, memory management. This system was very well optimized again, and it had a lot of small, short-lived buffers per emitter. But also the round trip that I just mentioned from CPU to async compute that's used to read back the bounding box of the emitter, spawn new sounds, and add lights to the scene for the next frame. So what was our strategy here? We mostly wanted to use fixed size buffers and sub-allocate as much as possible, so emitters would share the same buffer. And also there was some data initialized on the CPU in the PlayStation version that we couldn't really do, so we moved that to a compute shader. And the most important thing we did was actually move the simulation from async compute to the start of the next GPU frame, so we didn't have that dependency anymore. This does mean that our bounding box is a frame behind and sounds are a frame behind, but we do queue the lights directly on the GPU and use them the same frame. We had an issue with this batching because the particle state structure actually can differ in size between emitters because it depends on the actual expressions being used for the effect. So we cannot really batch them using a structured buffer like this. Luckily, we can use byte address buffer again to use templated loads and stores, and we don't really have to know the size in the shader using this approach. So after a lot of hard work, I finally had the simulation working. Couldn't see any particles yet, but I could see the bounding box. Because to view the particles, I actually need textures. And textures use a bindless system on the PlayStation that just copy all texture descriptors into a giant array and then supply an index to the emitters. On PC, on PC, we can directly use the resource descriptor heap for this. And that saves us setting up the array, but we have to be very careful because if we pass wrong data into this, we cause GPU hangs, which we did at some points in the project. And with all this in place, we finally have some particles, sometimes even a little bit too many. And we had some pretty big bugs as well. But after all this hard work on our render systems, this was the initial state that we started with. And after all that work, the same spot looked like this, a lot nicer. So with all this done, we hit our first playable milestone. And we have most of our render systems operational. The game is fully playable. We still had some limitations though at this point. We're still running the CPU and GPU in lockstep because we're dealing with some synchronization issues, mostly around the particle system at this point. And we still output a fixed 1080p resolution. Luckily, our team starts ramping up. We get people from other disciplines, and we finally get a real team. We get an extra graphics programmer. And we also visit the original developer in Seattle, which was really great. So now we actually need to convert this console port on PC to an actual PC title. And Yana will tell you more about that.
So we're going to need a few things to do this. Let's start with a resizable window. So at this point, the engine fully assumes a fixed output of either 1080p or 4K, and in fact, some effects straight up just crash if you go over this resolution. Thankfully, a lot of these resolution assumptions were fixed in a newer iteration of the engine, so that really helped us. We could integrate those changes. And now we just needed to make sure that we recreate all window size dependent resources whenever we resize, and we make sure to align our render targets to 8x8 to keep everything functional. let's have a quick look at compatibility. So most importantly, we need to be able to run on all vendor GPUs, and there are differences between them. As you can see, very wrinkly Taka only on certain GPUs. Very early on in the project, Marco and I actually decided to have 2 different kinds of GPUs in our own development machines, and that actually allowed us to catch bugs sometimes within a couple of change lists, which was really, really helpful in fixing them. Then we also need to make sure that we're running on the Steam Deck, both correctly, but also on performance. We need to make sure all of our shaders are wave size agnostic. At first, we had patched up the shaders to work with wave size of 32, which is very common, but in the end, we do support wave sizes of 8 to 128. And we ramp up with Compat QA, helping us catch a lot of very edge case configuration bugs. And speaking of configurations, of course, we need to make sure that our game is scalable. So we start by determining what our minimum supported specs are going to be, and then we get hard at work in designing our graphics presets, but also our graphics and display settings menu. And for this, at Nexus, we believe it's very important for the player to be able to immediately see the changes that they are making. And we also added a few new AO techniques because options are nice. To allow players to also tweak their render settings without causing performance issues in certain areas, we also wanted to allow them to enable dynamic resolution scaling. For this, we chose to use an alias render target approach. So we create a big heap that is big enough to store our largest render target, and then we create aliases within it, scaling down the resolution in small steps. We did try to handle this fully under the hood, so the engine doesn't really know about what kind of resizing we're doing. But it was pretty difficult to keep our PlayStation descriptors in sync with what we were actually doing under the hood. And as some of you may be familiar, if you've used alias resources, misplaced discards and/or clears can be a source of very, very nasty bugs and even crashes. For memory, there is a lot of popular consumer hardware right now that does have very limited video memory. And we don't really want to restrict the player with what kind of quality settings they choose. So to alleviate this issue, we do have the Nexus Memory Manager, which handles automatic memory movement between CPU and GPU memory, suballocation and defragmentation. And Hilza is actually going to go into detail on how this works this afternoon at 3 o'clock, so give that a watch. We also start ramping up on our graphics comparison meetings, and this is a concept that we do at Nexus that I absolutely love. We have a meeting room with 2 big TVs, and then we have the PC game running on one side, and then the retail PlayStation version running on the other side. We invite the entire graphics team and QA, and we try to find any kind of inconsistencies, small bugs, or room for improvement. To give a small example, at some point we had some green seaweed on PC. Well, that makes sense. However, turns out it was meant to be red, and that's probably something that we never would have caught if we didn't have these side-by-side comparisons. On to upscaling and frame gen. Of course, we had some issues with this. Velocities are very important to have correct for these techniques to work correctly, and not everything in this engine was outputting velocity. Thankfully, again, Sucker Punch helped us out. They had already implemented some new tech, which we could integrate, that gave us correct velocities, most importantly for grass. So that was fantastic. And now all that's left to do is support the latest FSR, DLSS, XeSS, and Menno is actually going to explain a bit more in depth about these techniques, but also how we approach them at Nexus on Thursday. For ultra-wide support, we did, of course, have to fix up some cinematics. Content is authored for 16:9 on console. Here we do need some art support. We can't, unfortunately, do everything ourselves. But interestingly, we could also trigger some very extreme performance situations. For example, 48:9 with our highest LOD setting caused so many objects to be visible that we actually hit some hard-coded limits in our engine that caused some nasty crashes. And finally, for PC, it would not be a real postmortem if we don't talk about pipeline state objects. For those of you who are not familiar, pipeline state objects encapsulate most of the render state that's required to execute a draw call, and they must be compiled at runtime on the user's PC. And if handled incorrectly, this can be the cause of the infamous stutter struggle. The typical Nix's approach has already been explained by Michiel and Rebecca in their Marvel Spider-Man Remastered PC Postmortem. But for a short recap, QA plays the game as they do. Whenever they hit a draw call that has a unique pipeline description that we haven't encountered before, we save that description to a cache file on disk. Then we collect all of these cache files, we merge them using an in-house tool. We read the cache file on startup, and then whenever we load in a shader, any pipelines that are associated with it get created on worker threads. We ended up using the same approach for this game. We were very fortunate. We ended up with around 16,000 graphics pipelines, which is very, very reasonable. We did make a few improvements. We could derive the shader hash from the material and its features instead of the bytecode, so we didn't have to beg and plead with QA to collect new pipeline descriptions for us whenever we made shader changes, which was often. And we also compressed the pipeline description, so our hashing was much faster. Of course, we also ran into a unique challenge, and that was, again, due to the particle system. So there were thousands of compute pipelines that were needed for particles, and because a lot of these shaders could be very complex, these pipelines were very expensive to create. So the first thing we ran into was we would get hitches whenever a particle system would get spawned, and we fixed this by making sure that we load up the shaders for the particle effects as early as possible, as many as possible during the loading screen, and then create the pipeline then. However, on our lowest spec machines, it was possible that this caused the first loading screen to be a few minutes long, so we added a message for the player to know what's going on. And then we also ran into hitches during traversal when particles would get streamed in, and then they would be immediately spawned whenever they were loaded. So on PC, we had to delay the spawn until the pipeline state object was ready, and we made sure to bump the priority of it so that we can spawn the effect as soon as possible. And speaking of hitches, let's talk about some optimizations.
Yes, a few months before ship, we were actually not in a super great state optimization-wise, especially CPU-wise, so we needed to do some optimizations. Here's an overview of some of the CPU optimizations that we did. We reduced the spin locks in the job system. Those are fine on console usually, but on PC they can really hurt performance. We also reduced the number of command lists that we had, because resetting them was also a big overhead. We moved the command list submission to its own thread. We made sure that the resource creation was also done on separate threads, especially for the texture streaming system. And we tried to reduce the number of descriptors we created each frame, because also descriptor creation was a bottleneck. We also tried to remove all the async compute round trips that were in this engine. And zoom in on that a bit. Here is the one for the proxy set with just an update, does some coarse culling on the CPU, then dispatches an async compute job that does finer culling, and then reads back the result and then spawns the draws for the next frame. Why is this so bad on PC? Well, the latency is much more unreliable on PC because of scheduling. Other programs can be running, so you're just not guaranteed to get your async compute results back that quickly. Also, on older hardware, async compute can be really bad, and this can actually really hurt performance. It must be said that on modern hardware, this is usually fine. So we had a couple of these in the engine. We already discussed the particle system, where we just moved the async job to the beginning of the graphics queue. We also had one for the read projected depth culling, and what we did here is instead of waiting for the previous frame depth buffer, we just waited for the one from one frame earlier, which made our depth culling a little less unreliable, but it wasn't an issue in practice. And for the proxy set culling, we tried to move it to the CPU, but this was way too expensive. We also tried to delay this by a frame, but we didn't really get that to work. And we also thought about moving it to the graphics queue, but that would lead to a lot of empty dispatch indirect calls, which is also not great. So we ended up shipping with this in the engine. But as I said, on most recent hardware, this turned out to be not that much of a problem. So for the actual rendering, we also did some optimizations to reduce the amount of buffer and descriptor creations. Our first native approach was just have a buffer per stream, per draw call. which resulted in thousands of these created and destroyed every frame, which obviously was pretty horrible. So when we got to the open world part, we did this optimization and just created views into larger buffers instead. So now we have a view per draw per stream. But this was still a big performance overhead because we still have to create these buffer views every frame. So what we did in the end was just have big buffers for each instance stream and use offsets inside these streams. For this, we actually had to modify the shaders and the system doing this, where we could do the sub-allocation on a lower level. But this really helped, and it massively reduced the number of descriptors we create each frame. And also for GPU optimizations, we ran into this thing with decal rendering, where it does a read, modify, write on the G buffers. There's a system in there that detects when decals are overlapping, and on console it just inserts a cache flush at that moment. But for PC, we cannot read from the render target. So what we need to do is make a copy of all the G buffers, bind the copies, and then read from the copies while we draw to the G buffer. And this turned out to be extremely expensive in some cases, because we had this situation where the sword has all these blood drops on it. So the first thing we did was making a specialized copy shader. This was more like of a band-aid, low-hanging fruit thing, where we would only copy the things we needed, and we would do it all in one go. Then the second thing we did was actually keep track of where the modification happened on the frame. So before the first decal was rendered, we do a full copy of all the G buffers. Then we keep track of what part of the screen is actually modified, and then only update that part in the copies that need to be updated. And this helped a lot. And we also skipped the copy entirely if it was small enough. For example, those blood drops are usually super small, and you don't really see if there's any render issues. Finally, let's get back to our SRT performance. How do we perform in the end with our emulation approach? Well, we definitely saw some performance overhead on specific hardware. Notably, NVIDIA really likes to have constant buffers. It can do better optimizations that way. And luckily enough, it was good enough to ship. There was overhead, but it was not too much, so we could still ship this approach. We also saw some real overhead from using our resource proxies, and especially when they were accessed inside of a loop. So when we had this situation where we have our resource proxy inside the loop, then we would take it out of the loop. Because otherwise, inside the loop, the resource descriptor would be loaded from the heap every time, and that would have performance impact. So finally, Ghost of Tsushima was an enormous technical challenge, but we really enjoyed working on it. And even though it sounded a bit crazy in the beginning, our PlayStation emulation efforts held up. We managed to keep our PlayStation build on our branch working during the entire project, and we only added a very tiny abstraction layer. And most importantly, we shipped this game, and we got really positive feedback. So we were really happy. Of course, we were not the only two people making this game, so I want to thank all the people that helped us with everything we did. That's our presentation.
In the grind, it's like, yeah, push up, yeah, go for it. Okay.
Shout them really loudly.
I'm not sure if this mic is working. Okay, and it's maybe off. Ja, ist das gerne? Du mic you on. Oh, it's on.
Okay. Yeah, the mic is on. We have, I haven't checked the schedule, but I think that we do have some time for questions. Raise your hand and I'll run around with a mic.
Yeah, hi. First of all, yes, looks very impressive. Also very impressive the amount of work you put into making it work on PC. And I was just wondering if you could go back in time and decide between keep it in sync, PlayStation and PC development in sync. Would you recommend that, or would you recommend this approach to do it afterwards?
I still think, in hindsight, this was the good approach for this project. I think for other projects, I prefer the setup where you already have the abstraction layer where you can just hook into, because this may be harder to bring over to like a newer, like if we want to merge it with Sucker Punch's mainline engine, for example, this approach is a bit hard to do that. But still, I think in this case it works all right, and I don't think if we would do another project like this, that we would consider a similar approach. Yes, of course we learn some things that we might want to do differently, but still, in the grand scheme, we would do a similar approach.
Hello. What was the timeline like that you guys worked with 2 people on the project, and then what was the timeline like when multiple people joined the project, and how many people were there?
So it started out with a small group when Bruce was there to set it up. Then it was about a year with the 2 of us until the first playable milestone, and then we had another year with a bigger team to make it a real PC game.
Hello, thank you for the presentation. I wanted to ask about particles, if you had something special or like had to implement something on top of for the upscalers, like reactive masks, composition masks, or motion vector, for the opaque.
Sorry, can you repeat the question a bit loud?
Sorry. If you had to implement something on top of the original work done for the particles in terms of the upscalers, like writing motion vectors for the opaque particles or composition masks, any special work for the upscalers?
For particles, we did actually run into a few issues that are not fully resolved. So if you look closely to the released game, then you will see some flickering related to particles if you use upscalers. And we have some ideas for improvements there. So if we ever do an update, then maybe that can be improved.
And okay, I see one more question up in the front. Hi, a question about your the constant buffer stuff on NVIDIA. Did you profile this also on RTX stuff, where it normally should be a lot better, I think? So it's mostly the low end.
It's worse on the low end, but it's still there. It's still there on RTX, but it's definitely worse on lower end.
So you wouldn't suggest? Yeah. Do you know numbers?
I'm not. No,
I'm interested. So. Because if you go minus constant buffers, you might hit the same problem, right?
I think that probably will be better.
Because of the byte buffer.
Yeah, I mean, we did work with NVIDIA a bit to see if we could get things improved, but in the end, we sort of ran out of time with the deadline. So there are definitely ways that this can be improved without going back to constant buffers. I think there were actually multiple issues here, but maybe we can talk after.
Another small question is for the PSO stuff. So you have your QA doing all this stuff. How do you find everything? Because the things that you go around and for shadows and things like that, things can be in shadow or not shadow. Do you auto create more by just putting them like for shadow shaders or no shadow shaders? And what happens if there's a miss? Is it an hitch, or do you do async and just dot draw it?
No, if there's a miss, it's actually an hitch, but we do tend to get a pretty complete pipeline cache because we have a lot of QA and we like merge all of their outputs together. And with this approach that we had on this project, we also don't hit a lot of cases where we invalidate the cache and need to recreate it. So it just keeps adding during the whole, during a large part of the project. So we are pretty sure we have.
Yeah, it works for a ship title, but of course, if you have like a live game, then...
we also do the thing that whenever you miss something locally, then it stores it at that point, so...
All right, so thanks Yana and Marco again. Okay. And